All right, welcome to our sixth and final video walkthrough of 2021 Advent of Code problems. In a couple weeks, we're going to be starting Advent of Code 2022. So I'll be doing daily videos for those problems as they come out. But this is the last sort of review video walkthrough that I'm going to do. We're going to do day 23 from last year. And this was a particularly interesting problem because it was a surprising use of Dijkstra's algorithm. So we come with this puzzle, but it doesn't immediately look like a graph problem. And basically our task here is to take all these tokens. I call them tokens. The problem calls them amphipods. That word is hard to type and hard to say, so I just call them tokens. But we have A, B, C, and D. And we're trying to arrange it so that the A's are in the left room, the B's are in the second room, C's, and then D's, like so. And we can move these tokens. Basically, there are a lot of restrictions about how they can move. We have this one hallway, but the tokens can't, they can't move past each other, and they can only move once into the hallway, and then their second move has to be into their appropriate room. So there are a lot of restrictions. So for instance here, this is just showing how a hypothetical solution could work. For instance, we take this one from B, we move it into the hallway here, then we take this C and we move it over here. Then we take D out of here, put it back up here, put this B down here so we get to this state. This B comes here. Okay, then this D comes up here. This A goes off to the side. The D ones end up coming down. And the A goes over here. And so we're trying to do this in the way that uses the least amount of energy. So each one of these, so obviously they're moving individual places, 1, 2, 3, and then 4, so that's just sort of how the moves work, and each of the different tokens expends a different amount of energy. So like A's use only 1, B's use 10, C's use 100, and D's use 1,000 per space that they're moving. So really you want to avoid moving the D token more than you really have to, because it's just a lot more expensive than everything else. Now the reason this ends up being Dijkstra's algorithm is that each state of this graph is like or I should say each state of the puzzle is like a node in a graph. And each transition step we can make, that's like an edge to a new node, and each of those obviously have weights based on how much energy is required for the move. And if we just use our final state as the destination, we can just use the shortest path algorithm to find the optimal solution. So that is what we're going to write up. So let's go into the code. This is pretty complicated program. There are a lot of moving pieces here, but let's start by just going over some of the types. We'll just make some simple enumerated types. We have tokens, A, B, C, D. We're going to have an enumerated type for the room A, room B, room C. That'll be useful. And then for each of the different hall spaces, so we have 2 halls off to the left, and then these other spaces and 2 halls off to the right. We don't count hall 3, 4, or hall 3, hall 5, 7, or 9 because we can't put tokens right above the rooms, so we can't put a token here ever. So it's only these other spaces that we're really concerned with. And now we can basically start constructing our graph type, or the graph state, a particular node in the graph. Each room will hold a list of tokens that's currently in there. Each hall space has a maybe token, either it has one or it doesn't. And then the graph state will also store the last move. We'll see how that comes in handy. And we also want to know the number of rooms that are full. So as we fill up a room and say, okay, we've got all our A's in the A room, then we'll increment this counter, for example. Just another couple helpful types. Room lens allows us to zoom in on a particular room in the graph state, just in a general way, so we can pass this as a function. So as a function from graph state to the list of tokens that we can pass to for accessing purposes. Same thing with a hall lens. We'll see how these work. And then a move. So no move constructor is just used at the beginning, because we store this move on the graph state so that we can always determine what happened. But every move involves a token, it involves a hall space, involves a room, and it involves a particular slot in the room. So, for instance, slot number 1 would be like the top slot in the room. This would be slot number 2. And the harder part of the problem, we have it goes 4 deep instead of only 2 deep, so we have 4 slots, 1, 2, 3, 4, and this just helps us measure the distance. So that's how we can look at a move. This Boolean on the move, all that really tells us is it'll be true if it's coming out of the room into the hallway. It'll be false if it's coming from the hallway into the room. So that is all of the types we're working with. Just a little more boilerplate that I want to cover before we actually get into the thick of it. So there are a couple of arrays we'll use. This is just telling us, okay, how much power is required to move a token 1. So just matching, A is 1, B is 10, etc. That's easy. The hall room distance is a little more complicated. This is just a constant array telling us, for a pair of the hall space and the room, how much distance is required to move there. So for instance, to get from hall 1 up to room A, that takes 2. It takes 4 to get to room B, and this is the space above, because then we'll add the slot number to get the final distance. And so we see how these increase. If we take, so hall 1, that's this space. If we wanted to get to room A, 2, 4 to get room B, and so on. Whereas if we take hall space 2, it's only 1 to get to room B, and then the rest of them, same sort of pattern. Once we get to hall 11, obviously room A is farther away, so you can see what's going on there. Finally, these split lists, last little bit of boilerplate. These basically say, okay, if we're in room A, what is the list of hall spaces that we will encounter if we go to the left? That's the first list. What is the list of hall spaces we will encounter going to the right? And we do this in order. So from hall A, if we go left, we either have 2 and then 1. If we go to the right, we have 4, 6, 8, 10, 11. And then B is just essentially offset. We go 4, then 2, then 1, and then 6, 8, 10, 11, and so on and so forth. These split lists will be very helpful. They just make some of the functions we're going to write a lot easier. And we want to keep them as constants. We could, derive all of these as a single expression using split at, but I think it's just a little more efficient to do it like this. Okay, so now let's actually think about how we're going to write this algorithm. All right, these are the 3 primary functions we're going to use, and these all have particular type signatures for a good reason. These are the functions we will use to pass to the Dijkstra M function, which it's just a library function that'll run Dijkstra's algorithm for us. There we go, that's its type signature. So state is just our graph state, and then cost is just an integer cost. So if you really took some time to look at it, all of these match up. This matches up with get neighbors. This signature matches up with get cost, and this one matches up with is complete. So these are the functions we'll use. We just fill them out one by one, and we'll actually start with is complete, because that's should be the simplest one for us to do. All we really need to do there, so we get our graph state as an input, we just need to check the number of rooms that are full. So if the room is full is equal to 4, then we're done. Then that's, this is a final state. This is how we know we've reached a destination. And we're sort of deferring work here. We're pushing work into our state updating functions. Now they're responsible for updating this room's full number. But I still kind of like this just because we'll be making this is complete call quite a bit. And so we want it to be very efficient, very fast. So the next thing we want to do is get cost. So normally you might have 2 different nodes and say, okay, what's the cost between these nodes? In our case, our cost just depends on the last move we took. And the last move is stored in the second state, so we don't really need the first state. We're just including it to make the type signatures all work out with the library. But this is all going to depend on the last move of our graph state. So if it's equal to no move, for example, then it's just 0. no move is just going to be what we use at the beginning. It's not really a move we're ever going to do otherwise. So aside from that, let's deconstruct the move now into the token and the hall space and the room and the slot number of that move. We're not going to use the flag, the Boolean flag, but again, helpful for debugging. So this is what our last move looks like. And how do we get the cost based on this last move? Well, first we have to get the multiplier for the token that moved. So we'll say multiplier token, or what we have to say, we have to take our token power array and get that value for the token. Easy enough. And then we get the distance. Again, we just reference an array, so we take our hall room distance based on our hall room pair, hall space, and the room. And then we just add the slot. That's how we get the distance that we're going. And what we return multiplier times distance. Very easy. So our first two functions are pretty small, but now we have to write the getNeighbors function, and this is really where all of the fun happens. So what happens in this getNeighbors function? So this has to take a particular graph state and produce the list of neighboring graph states, the list of states we can go to from this particular state. And we're also going to pass in the room size as a parameter to this function, just because that's the only difference between the easy part of the problem and the hard part. Easy room size is 2, hard room size is 4. So that's just an extra parameter. And this is a complicated function, or at least I should say room moves is really going to be where most of our work gets done. What getNeighbors is going to do, the way we're breaking this problem down is that, okay, we have moves that concern room A, moves that concern room B, C, and D, and so on. And so all this function is going to do is say, okay, get me all of the room moves for, room A. So we get room moves, and we have a bunch of different parameters. And also we'll get A moves, B moves, C moves, D moves, and we'll just return A moves, and just append everything. So this function, room moves, is responsible for calculating the moves either into this room or out of this room. And as we'll see, we can only ever pick one of those at a particular time, but it has a bunch of different parameters. So this function, we are taking the room size, we're taking the token that's associated with this room, we're taking the room signifier itself. I guess it's maybe a little redundant. We're also taking the room lens, so how do we zoom into the tokens that are contained in this room? And we will also take the split list that is associated with this room. What does this look like when we call it? So we say, for instance, room moves. Okay, so we always pass room size, A, and then room A, and the, let's see, it's the room lens is just going to be the room A, room lens. Again, seems a little redundant, and maybe it kind of is. Maybe I could clean this up. We're also taking the A splits list. And finally, we also pass the graph state. So that's what we're doing for all four of these. That's what distinguishes all these calls. These are just for B now. Okay. In fact, let's just go ahead and for these. Hopefully I didn't make any, didn't fail to copy anything, because I made that mistake a few times as I was doing this. So how does this function work? So for any particular room, basically we have 3 cases. So we're actually going to use a guard here. So case 1 is the room is already full, in which case, well, we actually don't need any moves out of here. No moves will actually get us closer to a solution. So what we do, we use our room lens to actually access the list of tokens in here. So we say room list on the state, and we want to know, okay, is that equal to replicate room size of the token? And if that's the case, the room is done. We can just return empty list. There are no more moves that there are no neighboring graph states that we need to worry about based on this room. So 2 other cases. So one other case is, okay, It's not full yet. It's not full of this token, but everything that is in this room is equal to the target token. This means we don't want to move anything out of this room because everything that's in there wants to be in there, but we may want to try to move the target token into this room again. So how do we say this? We say, okay, if all are equal to the token in the room, so again, we say room lens graph state, and again, this will work. This will return true if it's empty as well. It's another case to consider. We'll do something. Let's just say undefined right now. We also want to define that third and final case because what's in the third case? In the third case, we are dealing with, okay, there are some foreign tokens that are in this room. We want to get them out. So we're not going to move anything into this room. We're only going to move things out of this room. So that is what the third case is going to cover there. But let's not get too far ahead of ourselves. Let's cover this second case first. So in the second case, basically what happens is we want to search left for a token, and we want to search right for a token, because if we can go out of the room and search in either direction and find that token before we find any other tokens in the hallway, then we're actually good to go. Then we can actually move the token into this room. How do we do that? Well, first we're going to fill in this find x function. This will take the split list, it will take 1/2 of it at least, and it will search in that direction for the token. So how does this function work? Well, if we have an empty list of halls, then we can't find it. There's no hall space in this direction that actually contains the token, so we'll just return nothing. That's our base case. So now let's suppose we actually have something. So we have a lens into the hall space, and we have the space itself, and we have the rest of those lenses. What happens now? 3 cases again. So one is that, okay, if we use this lens and peer into the graph state, then what if we find our token? That means that we want to return this space. That we found it. This is a good space for us. What happens if it's a different token? So we say is just lens GS. So it's not just token, but it's a different token. Then we return nothing. Then we know we cannot find our target token by searching in this direction. So that covers that case. The final case, so it's nothing. Basically, then we're just going to recurse. So if we can visualize this, let's imagine that we just take this B out, put it just here. Whoops. Put the B just over here. And let's suppose we have an A over here somehow, but we have a C here. So if we search left, we will find nothing here, and then we'll find this B, and we'll say, okay, we can't do that. If we look here, we'll find the C, and we'll be like, okay, well, searching in either direction, we can't find anything. But if the C weren't here, we would keep searching, and then we would find this A, and we'd say, okay, this A potentially could move into this space. So that's basically what that function is doing. Just sort of reset the grid there. Okay, so let's now use our find x function in both directions. Okay, so we want to say left. Okay, so maybe left, we will find x, looking for our token, and the state with the first list the splits. Remember, that's our left side. And then we'll do the same thing to the right. This just uses the second split list. So these are our 2 candidates. So now for halls, we'll just say cat maybes based on these 2. So we'll say maybe left, maybe right. And we'll get that a value. And what do we want? So now we also want the slot number. So if we're moving it into this room, we need to know which slot we're putting it in. We take the room size and we subtract the length of the number that are currently in there. So for instance, if there are 0 in there, we'll take room size minus that, and we'll get 2. That's what we want. That's the amount of distance that we would need to travel. So that gives our slot number correctly. And then we can go ahead and construct the moves, all of the moves associated with these hallways. So we just map a function over these halls. And so based on the hall space, we'll construct a move that involves the token, because obviously moving a token into this room, it must be the appropriate token for that room. And we'll use the hall space, and we'll say the room and the slot. And we'll say, because we're moving into the room, we'll just say false here. And now, what do we do? So we need to apply these moves, and we'll get to that part later. But in this case, we're actually going to use the function apply hall move. So we'll return map apply hall move, and apply hall move will need a bunch of these parameters as well for reasons that we'll see once we get there. Did I even do that right? Apply hall move, room size. It doesn't need the token apparently. It does not need the token. So that's all good. So that will cover that case. Once we get to these application functions, we'll write those two together because they sort of make sense together. Let's look at the third and final case of room moves before we do that. So the other case is we are moving the top token in this room out. So, for example, we can deconstruct this and say, okay, let top room and rest room be a deconstruction of the tokens in this room. So it's important to note here that down in this case, we cannot have an empty room anymore because otherwise this would return true. So we know that this is a safe operation. So we can get the top element in the room. Let's also get the slot number that we're moving from. In this case, we want to take room space minus the length of the rest of the room. So for example, if we have 2 items, room size is 2, we have 2 items in there. The slot number we want is 1, and so we take room size 2 minus 1. 1 is the length of the remainder of the room. So now we take halls, and now we're actually going to find a new function that we use, and that is the find empty halls function. So what is this going to do? This is going to search for my room and find every empty hall in a particular direction that we could conceivably move the token into. How is this implemented? It's actually not too dissimilar from the find x function. We're again just doing a sort of recursive loop. And so what are we doing? This is actually an accumulator argument. We'll do it tail recursively and just accumulate the valid hall spaces that we can use here. So base case is that we're out of new spaces to explore, in which case we'll just return our accumulated list. We don't actually have to worry about reversing it or anything because the order doesn't matter here. But now let's once again assume, okay, we've got our lens. Whoops, this isn't right. We've got our lens, and we'll append to the rest. And now, okay, so if something is in this space, then we're done. Then we can't go any further in this direction, so we'll return our accumulated list. Otherwise, it's an empty space, and that means we can actually append it to our list. So we'll say find empty halls, and we'll append it to our accumulation, and we'll just recurse on the remainder of this. So that's find empty halls. Now let's go ahead and apply that to, find the empty halls that we can move in this direction. So we'll say halls is equal to find empty halls. First on the splits, empty for tail recursion, and then we append that to the same thing basically, except we are now using the second half of the splits. So these are, left-sided halls over here, right-sided halls over here, and that. So what do we do with that information? Now, again, we'll do the same basic pattern here where we will construct our moves here. So we'll say moves equals map, lambda hall space, move. And so what token are we moving? We're not moving this token necessarily. We're moving the top token in the room. And we're moving it to that hall space specified. We are moving it, or I should say the move involves the room. So we're using that same argument, and we're using the slot that we've calculated, and this time we'll say true, and we'll map that over our halls list, and finally we will return apply room move over these moves that we constructed. And again, I think I determined that we do not need the token now. It's not necessary. Okay, so the last thing we really need here is these apply functions. How do we apply a move that goes into a room? How do we apply a move that goes into the hall? We'll actually start with apply room move. I think that one ends up being a little bit simpler. So we'll go ahead and say, okay, if it's no move, so we say, you know, if it's no move, this is just the original state, no change. So we need to calculate, like I said, the new graph state involving this move. So now let's assume we have M. We want to save our move because we'll save it in the new graph state. So we'll say token, and we'll deconstruct all of this. So we're going to do 2 modifications to the graph state. We'll see why this happens. It's just there are multiple case statements. We'll do one case on the hall and a second case on the second case is basically happening on the room that is involved here. So we could just do one case statement theoretically, but there would just be a lot of cases. It would end up being like 30 cases, and I don't want to do that. So, so say let GS2. So based on the hall, if it's H1, then we have to use a separate lens here. So we say hall 1 is equal to just a token, because we're moving this token into the hallway. And we're saying last move is equal to M. And we repeat this for the other hallway cases. So 4, 6, 8, 10. So we change the hall designations, we change these lenses. And that's all that really changes in this first modification. Now, in the second modification, we say, now we have to look at the room. The room that we are moving the token into, out of, in this case, sorry, we're applying the move out of the room. And so if that's equal to room A, now we have to modify what is in room A. And we actually have to say tail. So we have to, remove the head from that list. Whoops. So now we've made our second modification, and this is the final modification. So we modified the hallway by placing the token there. We modified the room by removing its head, and we modified the last move by placing it there. Now, we're going to do basically the same thing when we apply a hall move, except it's a little more complicated. So we need the room size. We'll see why, because this, when we apply move from the hall into the room, now we have to keep track of the finished count. So that's why we need all of these things. So we need the room lens, the graph state, and if it's no move, again, state, complicated, no tricks. But if we have move, token, hallway, room, slot, same basic process. And copy that correctly. So we make one modification where we modify the hall. Except instead of saying just token here, make it nothing, because we're modifying, moving it out of the hall and into the room. Okay, so now what comes after this? Except there's, I should say there's one more step we want to add, which is we want to calculate what the new finished count is. So how do we do that? So whether or not it is finished, this is equal to, so we have to look into the room of this graph state, and if it's equal to the room size minus 1, then we are finishing this room. And so the finished count, the final finished count, so if we're finished, then it's rooms full graph state plus 1, else it's rooms full graph state. That's easier to write. It's actually easier to write that as plus is finished. Okay. A little bit easier there. And so we'll also want to make this modification here. So we'll say room is full is equal to the finished count. And now we need to make just the modification in the room itself. So we'll say based on the token that is moving. And let me actually think about this because, yeah, it's the token that is moving. If the token is A, then we get room A, we append room A to GS, to the original room A from the GS. And we do the same thing. And we do the same thing for all rooms. Seems like I might have, oh, whoops, this seems to be okay. So that should finish the algorithm. There's a lot of code here, a lot of ways I might have mistranscribed it. So let's go ahead, test it out, and fill in our functions up here. Just a quick note, we have this is our description of the initial state, nothing too complicated. Like if we just look here, you know, first room is BA, second room CD, BC, DA, etc. So nothing too scary there. With the more advanced states, it just has 4 in each room. That's all we're doing. And these two functions will basically be copies of each other. So what are we going to do? We want to use our logger. So say run standard out log t. And we will say we get a result, call Dijkstra m with all of our nice components. So we say get neighbor. Remember, we want to partially apply get neighbors based on the room size. So we'll say get neighbor 2, get cost is complete on the graph state that we're input based on the result. You know, nothing. It's just the distance and the path. That's kind of nice that we get the full path from this. Then we can just return just the distance. And that is basically the same thing for our hard solution. And so we get 4. Now, some debugging revealed subsequently that I made a mistake in my application functions. Very important to use GS2 down here instead of GS, because obviously we want to take our modified state and rather than modifying the initial state, which will result in none of these moves happening. So that is that's kind of what happens. So let's go ahead and run our code. And we should be able to run A23 with this small case, and we'll see the answer we expect here is, I believe, 12521. That's what we get, and my answer here on the actual puzzle input that I was given was 10526. And we can see this takes a little bit of time. It's not an instant solution, but we're still gonna get it in probably under a minute. So this is for one of the later problems in Advent of Code. This is actually this is pretty good. If you're getting it under a minute, that's pretty solid. They tend to have a pretty high scale, and the scale of this problem is pretty large, but it's not intractable. So eventually we will arrive at our solution, and we see that's 10526. And I'll do one more example just on the hard part with the depth of 4. We would expect, let's see, so 44169 is sort of the easy case if we do so hard, and the small case, that's the answer we expect. Again, it's bigger, it's going to take even maybe a little more time, but still, we're kind of hoping, about a minute on this solution. So we'll let that run. In the meantime, I'll do the wrap up here. If you are enjoying our video walkthrough content, I do encourage you to subscribe to the YouTube channel and also subscribe to the Monday Morning Haskell, the monthly newsletter. That actually has a major bonus that will be going out next week. You'll see if you are a subscriber and you come to the blog site. We've got a big offer going out next week, so you'll want to make sure you do that. And of course, the code for this problem, I have it all on GitHub, so that's linked in the video description. There's also a link to the original, the in-depth write-up on the blog. You can take a look at that as well. So all those links in the video description, and we finally got our answer, 44,169. So we know that this is working correctly. All right, thank you so much for watching, and I will see you on December 1st when we'll be starting Advent of Code 2022.